Please join me in welcoming to the Distinctive Voices podium, Dr. Daniela Oliveira.
Thank you so much, Jennifer, for the introduction. Good evening, everybody. It's a great honor for me to be here. So today I'm going to talk about my research area, cybersecurity, the challenges and the frontiers in this field that you're going to see. It's very, very interdisciplinary. So we are living in a society that is completely dependent on networked computer systems. So power plants, they are completely managed by computer systems in a networked environment. Now we can have medical devices implanted in our body that communicate wirelessly with our healthcare providers. We have cars, refrigerators, TVs that are networked. We do e-commerce, we do banking, we even do social networking using the networked computing systems. And we have people at least have 3 devices, like a mobile phone, a laptop or desktop, or an iPad. So it's not surprising that these systems now are a target for a never-ending war against their resources, their infrastructure. So just as an example, so let me show you here this very interesting application that shows online what's going on right now in terms of cyber attacks in the world. So this application here, they have a set of what they call honeypots, which are machines that are vulnerable, and they stay pretty much waiting to be attacked. It's not a problem that they are attacked because they don't have anything interesting, but it shows what's going on right now as we speak, our country being attacked and attacking pretty much a lot of attacks coming from Asia, from Europe. It seems like the southern hemisphere is not very active in cyber war, but that's the picture that we have. So prior to 2000, this was the profile of the attackers. They were young, male, and they didn't have a commercial interest. They did this to make a point, to have fun. But now things are very different. So who are the new attackers? They are nation states. They are groups interested in cyber espionage to steal intellectual property from organizations. They are organized crime. So organized crime always go where the money is. And insiders. So now you can have situations where a disgruntled employee can cause a lot of losses to organizations, or even people that are planted in organizations by cybercrime or nation states. And cybercrime and cyber attacks, they can have devastating consequences for our society. So first, it's the cost, the amount of money being spent on cybersecurity, like companies buying approaches, investing in cybersecurity, it's on the billions of dollars. Imagine just using this money for, let's say, curing the cancer, investing in education, in health for our society, instead of having to worry about that. Cybercrime is estimated in $1 trillion, the cost of cybercrime. Why I'm saying estimating? Because organizations and nation states, they are reluctant to disclosure their losses, their attacks, if they are blackmailed, because this could affect their reputation. So this is an estimate. And then you can have situations where a nuclear plant, like attacks like Stuxnet, where a nuclear plant was stopped. And this attack here, that's very important because, see, we see for the first time as an official state of cyber warfare for our world, where Russia officially attacked Estonia through cyber attacks. And you can have headlines like that. So other types of consequences. So just last June, this summer, I'm not sure if you guys heard of this security breach on government employees. So this cannot be undone, right? Their sensitive information was disclosure. How can we undo this? And we have sensitive information from organizations, from countries being leaked, which can cause great damage in terms of diplomacy and even the relationship with the country and its citizens. And scary headlines like that. For example, now we have our data, digital data, including health data, is stored in remote computing in what they call the cloud environment, where we have no guarantees about how they're managing this data, what level of security. And right now, our health, our sensitive information related, let's say for our health, even our DNA information can be leaked, and scary headlines like that. What happens if some vehicle is attacked or a hackable medical device? And the challenging is that this is an unfair war, because it's much easier for an attacker to attack than a defender to defend. It's much easier to find a flaw, a vulnerability into a computer system than to design and implement and test this computer system without any flaw since the beginning. So attackers, they usually have an upper hand. So I talked about this motivation, what was the devastating consequences of cybersecurity, but how can we define cybersecurity? Cybersecurity revolves around these three pillars, which in our community, we know these pillars by the acronym of CIA: confidentiality, integrity, and availability. So these are our goals as engineers and scientists to achieve cybersecurity. We're talking about these three pillars. So what's confidentiality? So confidentiality has to do with keeping sensitive information or sensitive functionality only available to authorized parties. Only authorized parties should access this type of information. Integrity. Integrity has to do with preventing data and the system from being tampered with. So one classic example of a breach of integrity is a virus infection. So a virus, like its biological counterpart, infects other files, so tamper with other files, so that the other file starts performing malicious actions and infecting other files. Pretty much like a virus does with our cell, uses our cell to produce more virus and infect more cells. Availability is the property of the system to respond to its legitimate clients in a timely manner. So an attack on availability prevents the system from achieving that. So a classic attack on availability, it's what we call a denial of service attack. So in an attack like that, what happens is that malicious hosts, they exhaust the resources of a legitimate server in a way that when legitimate clients come to request access to the server or to try to use the service of the server cannot serve. So the availability was compromised. So what's the current state of the art? So the news is not that bad. So cybersecurity is a crowded area in terms of research, is a well-funded area, priority of our government. So there are a great number of researchers and research groups across the country and also across the world investigating how can we make the cyber world more secure. So, and the solutions, they involve all the layers that make up a computer system. So if you think about a computer system, we have the hardware as the lowest layer, followed by a virtual machine or a hypervisor, and an operating system, which is like a government, a supervisory software that mediates the access to the hardware by applications. Applications cannot access hardware directly. We have the network also. So we have, for example, solutions like firewalls, where the traffic in and out an organization, for example, are filtered and controlled according to rules. We have packet inspection techniques that perform like a scan of network packets, and the goal is to observe these network packets and see, do I see any signs of malicious signatures that I have seen before? If so, I should filter these packets. There are solutions at the hardware level. So hardware Trojans are malicious logic at the hardware level. So this is very challenging for researchers, especially because our hardware, the fabrication of our hardware, it's outsourced, is not done in our country. So we have no control of what comes in and how to test this. And when you say we, I'm not talking about us as citizens. I'm talking about the computers that run at NSA, that run at the White House, that run at the CIA. So it's a huge point of vulnerability for cybersecurity. We have solutions at the operating system level that mainly try to prevent the operating system from being tampered, the idea of integrity, because the operating system is a supervisory software. So if it's tampered with, it can affect all the applications. At the application level, we have signature-based intrusion detection systems. So as the name says, it's based on signatures. So this approach, they have a database of what malicious software that they have seen before, and they try to match new software, new process according to what they have seen before. So they have a great accuracy, very good accuracy, but they cannot recognize new attacks. On the other hand, there are solutions that use machine learning that try to build a model based on a training data of what's benign, what's malicious. They don't have a perfect accuracy like signature-based detection, but at least they can counter new attacks. So what's going on? When you look at this landscape here, we see that all these solutions, they usually work in isolation. They do not communicate, they do not exchange information, and researchers, they're starting to realize that's not a good idea. So where do they go to get solutions? So we go to look for solutions, especially in biology. We like to compare cybersecurity with biology, and especially our immune system. Our immune system is under attack every day, and it does a pretty good job at keeping, like, of course, we can die for infections. It might fail, but overall, it works pretty well. So let me give you an example of a line of research that tries to get these ideas from biology. So operating systems have a challenge. So all the time we have to install new extensions to the operating system. Let's say you buy a printer, okay? So you guys probably, many of you have installed the driver of the printer, right? So the driver is a piece of software that allows your applications to actually talk to the printer, okay? And this driver is installed as part of the operating system as an extension. And it has access to anything inside the operating system. So it works at a privileged level. But the problem of extensions is that they come from a third party. So Windows or Linux, they have no control of this code, okay? So, and they represent about 70% of operating system code. So it's a huge portion of the operating system. And they are very convenient. They extend functionality of the operating system in a convenient way. But there is a problem. Some of them might be malicious, might be vulnerable, might be buggy, and might allow attackers to exploit the operating system through them. So it's a paradox, right? The operating system must co-live with untrustworthy but needed extensions. So if you think about our immune system, it also faces the same problems. Our body has 10 times more bacteria cells than human cells. So we are a superorganism, if you will. And these bacteria, most of them, they are not only benign, like they don't harm us, but they are needed for a set of physiological functions in our body, like they control digestion, obesity, autoimmune disease, so the body needs that, the bacteria. But there is a problem. A small fraction of them might cause pathologies, might make us die or make us feel sick. So how does the immune system do it? The immune system evolved to maintain this healthy relationship with our microbiota. And the idea is to control the interactions with the tissues. So, for example, the immune system keeps them in very confined environment, and there is a layer of mucus that tries to keep them out. And if they try to get out, they are killed. So that's the same idea that researchers are using to protect the operating system. How can you confine these extensions in a way that they can still perform their job, they still have privileges in the operating system, but they are confined? So that's what's going on in terms of research in this area. Another important aspect of cybersecurity is that we usually think that cybersecurity is about computer science and engineering. It's about technical solutions. And we forget that human actions, my community likes to call it errors, account for most of the security failures. Isn't it amazing? It's not a breach in the antivirus. It's not a breach in the detector at the operating system that caused the most breaches. It's human actions. For example, social engineering that can be transferred to the cyberspace. Poor user interfaces, let's say interfaces that tries to help us to increase the security or to use a security solution if we don't know how to use them. So what's the protection? Security requirements beyond human capabilities, like passwords that we have to change every day with so many difficult security requirements. And the lack of economic incentives from users and also from software developers to think security. As an example, the burden of passwords. So research shows that consumers, on average, they need to remember 25 passwords with very complicated requirements. And even myself, as a cybersecurity researcher, every year at the University of Florida, like I come up with a password that I can remember that is about all these requirements, and then 1 year later, they ask me to change. And I get so mad because it took so long for me to think about something that's secure and I can remember that I don't need to write down. And then I need to change. So it's a burden. Maybe it's beyond our capability, these requirements. And we ask so much and we end up with things like that, with insecurity, with people writing down passwords and just posting the password in their cubicles. And there is a good body of research where researchers are trying to discover memorable passwords. How can you help users with memorable passwords? How can you help users manage passwords in a secure way? Ideally, you would like to have a password manager that takes care of all the passwords for us in a transparent way, but secure way. So there is a lot of researchers working on this area. Warning design. So I think most of you already received or saw browser warnings like that, right? So for example, this site, security certificates not trusted. So to my dad, this is Greek, right? Site certificate. He doesn't understand what is this. So for the average user, what's a site certificate? The person needs to understand that a protocol called secure socket layer is being used and needs to understand all the idea of public key crypto system to understand what this warning is about. So researchers at Google, they did this study here when they just change, they use warning science, and they just slightly change the message, and they increase the compliance of the warning from 30% to 60%. So this is very important. And of course, humans can be influenced. Regardless of our age, our background, our level of education, there are several, what psychology calls weapons of influence, that make us work and behave and make decisions in an automated fashion. One example is authority. People tend to comply, to say yes to requests made by figures of authority. So one example, a real example, is Chinese spies. What they did, they created this fake Facebook profile for the U.S. Naval Admiral James Stavridis. So it's a fake profile. He never created a Facebook profile. And this fake profile started befriending NATO officials. Who wouldn't befriend with him, right? And see the dangers of the situation. So now this fake profile have access to very private information about these officials, like their pictures of their kids, what they do, where they live. And this can be used in social engineering attacks. For example, this James could send a message, and this message could have, let's say, a link, and this person might click in this link, and malicious software might get installed in the computer. Now imagine if this computer is inside the military or inside an organization. So in the second part of my talk, I'd like to talk a little bit about two pieces of work on my lab. The first piece has to do with the technical solution, operating system security. And the second piece, in contrast, looks at the human factors of computer security. So the first piece of work, we got inspired by warfare strategies. What can we learn from warfare that we can employ in cybersecurity? And that's what we are doing. We're building an operating system that actively defends itself through deception. So our computer systems are highly predictable. We live in a software and hardware monoculture. We have a few operating systems, a few hardware architectures. Everybody pretty much uses the same software. And this has a lot of advantages. This streamlines the software development processes, deployment, testing. Developers call this write once, run everywhere. But it also poses some security problems. So now, if an attacker finds one vulnerability in one application, in one operating system, it can exploit this vulnerability in thousands of systems of the same type. So a classic example was the Code Red worm in 2001, which was a vulnerability in a Windows service. So in a few hours, pretty much the entire world got infected, and it caused billions of dollars in losses in a few hours. Another example here is this graph here from DARPA. And it shows, so this is the increase in security software in lines of code since the mid-'80s. So as you can see, exponentially. And see, the average malware remains in lines of code low and constant. So that's clearly something really wrong here. They are having an easy time. So what can you do about that? So then we thought, what if we could make systems less predictable? And it's a challenge, right? Because unpredictability affects functionality. So what can we do? And again, we got inspired by war strategies like Julius Caesar. So usually this greatest war strategists, they won their battles by surprising their adversary. So we started thinking about the idea that what if we could have this operating system that embodies this paradigm of trustworthy unpredictability. So the idea would be for good uses of the system, known uses of the system, whitelisted uses of the system, the OS is predictable and efficient and works according to the specification. But for unknown uses of the system, let's say everything else that might bypass, let's say an antivirus might bypass a firewall, the operating system should be unfavorable to this type of software. So we're building Chameleon. Chameleon is an operating system that, as a chameleon, changes its behavior depending on what's going on in the system. So the idea is that for mission-critical software, let's say software that's critical to somebody, to a person, to an organization, software that is known to come from a reputable source. This software runs in this, what we call this diverse environment. In this environment, there are no losses, there are no, everything works according to the specification, but we provide different implementations of the same functionality. The idea is the following. If an attacker is relying on exploiting one particular vulnerability from an operating system functionality, it cannot rely on that anymore because another implementation might be used. So we are trying here to increase the diversity of the system. Everything that's unknown runs in this unpredictable environment. And here we employ inconsistent deception. We create an environment that's unfavorable, that's foggy, where some losses will occur. Like the process can still run, but it's going to be unfavorable. And finally, if we find that the software, the process, is indeed malicious, we run this process in this deceptive environment that applies consistent deception. So here we provide a false front, a facade. And the goal is to lure the attacker into revealing its strategies while we collect forensics information. We also employ, to make Chameleon make more accurate decisions, we employ a machine learning module that on the fly dynamically tries to figure out if a process should be moved from the unpredictable environment in case it's showing signs of actually being benign, or to the deceptive environment if it's showing signs of being malicious. So let's imagine a typical scenario. Let's imagine Bob, 78, living in a retirement community in Florida. So Bob, so these are a summary, a very, very summarized version of his computing needs. Bob uses Microsoft Office because he's highly engaged in his homeowners association. He, of course, uses a browser and an email reader for news, for email, and every Sunday he talks with his son in Illinois via Skype. Bob is not computer savvy, and he might receive phishing emails, and he might click on this link. And this link, by clicking on this link, this attack might install malicious software in his computer. But the problem is that this malware, Bob never notices because the malware is smartly engaged only after 1 a.m. He's sleeping, so he never noticed that. So what would be a scenario where Bob runs his system on Chameleon? So all software that's mission critical for Bob will run here whitelisted. So there is no losses of functionality, so he still can achieve his computing needs without frustration. But if Bob decides to download a game somewhere in the internet, and this game turns out to be a Trojan, what happens is that this game is running in this unpredictable environment. So there are going to be some losses of functionality. Let's imagine that this Trojan is trying to connect with an attacker remotely. It might lose some bytes. It might lose some commands. And what happens is that Bob's safe because the Trojan is at the minimum handicapped. So what did you do? We selected some unpredictability strategies to be applied. And as examples, we could, for example, silence operating system functionality randomly. We could change data input. Data input could be lost. Like a part of the input could be lost. We could add noise to the input. We could just pretty much empty the data buffer. We could add delay to the functionality. We could change some parameters of a network connection. And we could change, like for functionalities that deal with files, we could change the file pointer. So this is an example of the subset of the system calls, the operating system functionality that's selected. So we did a study on a set of malware and benign software, and what we found is that benign software tends to invoke a more diverse set of functionality, while malware tends to invoke a more narrowly set of functionality. And malware tends to be what we call I/O bound. Malware tends to do a lot of input-output, like connecting to a network source and sending and receiving bytes, writing into files, while benign software might be a mix of it. So we selected a set of system calls, a set of operating system functionality that was more relevant to malware than benign software. And we analyzed, so these results here are only for the unpredictable environment. So we ran malware in the unpredictable environment, a set of malware from several categories. And we also played with the unpredictability threshold. So, for example, an unpredictability threshold of 10% means that the probability of one of the system calls here being perturbed is 10%. So it's a very low unpredictability threshold. So as you can see here, for the very, very low threshold of 10%, on average, malware could only function, could only achieve its mission on half of the incidents. The other half, malware was either completely neutralized, so it could do anything, or it was handicapped. So what do I mean by malware being handicapped? So 2 examples. One example could be a virus. A virus, in this case, infected another file, and what happened was that that file that got infected corrupted because of the unpredictability. And we think this as a winning situation because, yes, the file corrupted, but at least it cannot infect other files in the system. Another example that we observed was a botnet. So a botnet is a jargon in cybersecurity for a compromised computer. So imagine that I'm a victim of a social engineering attack. I clicked on a link. Malware got installed in my computer, and now my computer is a compromise. My computer is a zombie. My computer is accepting commands from an attacker, and let's say sending spam to other people and being engaged in denial of service attacks. So what happened in the handicap case? The compromised computer lost commands from the bot herder, or the compromised computer sent less spam. So now the attacker needs much more resources to achieve the same goal. So we increase the work factor for the attacker. We also analyze the effects of unpredictability on benign software, on a set of benign software. Of course, this software, the whole goal would be that they would run in the diverse environment, whitelisted, but we were curious about what would happen if we ran them in the unpredictable environment. So what we saw is that benign software is much more resilient to unpredictability than malware, because benign software invokes a more diverse set of functionality. So as you can see, for the 10% unpredictability threshold, only this text editor here showed errors on 20% of our experiments. So it's a very encouraging result that malware is much more affected than benign software. So, and this was for what we call I/O-bound software that does a lot of I/O. We also test CPU-intensive software. CPU-intensive software provided a very interesting case. So for CPU-bound software means that they do much less I/O and they do much more processing. The CPU is always executing instructions instead of actually exchanging data with files and networks. So for this type of software, the percentage of system calls from this software that suffered perturbation is much, much less than I/O software and malware. But on the other hand, any perturbation caused them, like they are very sensible to perturbation. So as future work, what we plan to do is to find a way to filter them out. And it would be a reasonable assumption because malware is usually I/O bound. So from these results, what our remarks was that a holy grail of system design is the capability of thwart attacks with less effort than they have to generate attacks. There is no silver bullet, so we cannot come up with a solution that is perfect, that completely protects the system. But if you make the attacker increase its work factor, increase the cognition, effort, the time that it takes to achieve the same goal, it's a winning outcome. And chameleon and unpredictability and active defense achieves this goal because everything works as if every run of the system is different, is diverse by design. And so that's what we are investigating more, how we can fine-tune this, how we can protect more benign software. So the second piece of work from my lab that I brought is completely different, has to do with the human factors of computer security. And I did this because I wanted to contrast these two sides. So this work is about how psychological heuristics can explain software vulnerabilities and how priming developers can illuminate their blind spots. So the idea is that we should not expect developers and even users to go and make the effort to seek security information. We should bring security information to them when they need it. So vulnerabilities are increasing, software vulnerabilities. If you read these reports, Symantec, McAfee, every year you see that the number, it's always, every year, it's a good number of new vulnerabilities in software. And something that is very interesting is that the same old, well-studied vulnerabilities are still common. Let's say, for example, this vulnerability called buffer overflow. This vulnerability has been studied since the mid-90s. And there are papers, approaches, guidelines on how to understand and prevent. And this is October 2015. And if you go to any of these vulnerability databases, you see a new version of a buffer overflow. And this puzzles the security community. And what do? They blame the developer. It's the developer's fault because there are so many guidelines available. There are so many security classes available. Why the developer is keeping making the same mistakes? Doesn't make sense. Go read my paper, right? That's the solution. So we looked at the problem from a different perspective. So psychology shows that we human beings, we have been hardwired since evolution for heuristics. And this is an adaptation because our working memory is short, and when we are confronted with so many information, like this guy here, so many information, so many possibilities, so many options, we get overwhelmed and we make bad decisions. So when you think about developers, when they're coding, security is usually not a priority. They are thinking about shipping functionality. They are worried about time to market. Who gets to market first? Gets the consumers. They are worried about their deadlines. They are worried about performance. So security, it's usually not something that's in their working memory, let's say. And this is very interesting because vulnerabilities are usually hidden in corner cases. So we have this contrasting scenario here where attackers exploit these corner cases exactly because developers don't pay attention into these corner cases. So our hypothesis was that, okay, we believe that vulnerabilities are actually blind spots in the way developers make decisions. So we did a study with real software developers. And what we did in this study is that we gave them 6 programming scenarios that we call puzzles. And each one of these scenarios had a classic vulnerability, like the buffer overflow vulnerability. And they never knew that the study was about security. We manipulated them in the sense that we just said, oh, it's about, we want to discover how developers think in a general way. And in this study, we progressively cue them on the spot about the possibility of problems, unexpected results, or vulnerabilities. So in this study, we worked with 3 information conditions. So one was a control condition, where they didn't receive any information. The second, when we primed them in a gentle way, very slightly. And the third one, we explicitly said, oh, this puzzle has a vulnerability. What's this vulnerability? Why developers make this mistake? And each one received 6 scenarios in this order. So the first 2 was control, priming, and explicit. And the order was random, like developer 4 could receive scenario 4 as control. So our independent variables, the variables that we tweaked, was the vulnerability scenario, which classic scenario that we worked, and the condition. And we want to see, like our dependent variables, what the survey score, how well they performed in the security questions. So this was one example of a vulnerability that we worked with them. Is a recent one, was the only one that was recent in the pile, the Python SSL vulnerability. And this vulnerability has to do with the fact that this function here in Python, from the Python library, doesn't check the certificates in an SSL connection. So the SSL protocol, for those that are not familiar, is the protocol that we use to perform e-commerce. So when, let's say that the server is Amazon, and here's my browser, this protocol allows me to know, yes, I'm talking to Amazon. It's not a fake website impersonating Amazon. And number 2, all the information, my credit card number, everything that I'm exchanging with Amazon is encrypted. So the part that they know that it's Amazon is through what's called a certificate that's issued by a trusted third party that we call certificate authority. There are very few that issue the certificate, and there is a way inside the operating system using public crypto key systems to verify that, yes, this is a valid certificate that comes from a certificate authority, and yes, this is Amazon. So this function here, even though it takes as an input a certificate file, it doesn't check certificates. So it's a blind spot. Developers, they assume that the function checks the certificates. And this could cause a server in a class, server impersonating another server to a developer. It's very dangerous. So this fake server could steal credit cards, information, sensitive information. So in the control condition, we ask some warm-up questions like inputs, what happens, and we also gave a task for the developer to do. So why did you do that? We were checking whether a developer that knew that this piece of code had a vulnerability would go into the trouble of fixing the problem. And this is a very common situation in software development when developers give maintenance to code, right? So what do? Would they fix? In the priming condition, we ask all these questions here, plus we prime them. We ask if a developer could experience unexpected results, and what would be examples of these unexpected results. And in the explicit condition, we explicitly said that the code had a vulnerability. We asked what was the vulnerability and why the developer think developers have issues with this vulnerability. So we graded the answers by 2 independent researchers. We also had a debrief where we told them, okay, what was the purpose of the study? We asked about not only questions on clarity, but also if they were suspicious about the nature of the study, if priming had any effect, if changed their mindset. We asked about their security experience, education. We asked if they knew all the vulnerabilities that we used in the study. And this is the breakdown. So most of them are from the industry. 11% were in positions of software management testing, but they worked before as software developers. And we also brought some developers from the academia. Most of them male. There's some issue here with my picture. I don't know what's not showing. But most of them are male. Almost all of them had a degree in computer science, computer engineering. Most of them didn't have a security class, and average age around 31 years old. So this is the results that we got for the accuracy of the security answers to security questions according to the information condition. So as we prime them, they start paying more attention. As we prime them on the fly about the problem, the accuracy improved. And the cases where it didn't improve is because they never learned about the vulnerability before, so they had no idea, actually. And we also studied these very interesting scenarios here. We are interested in knowing, for example, for developers that explicitly said that they knew the vulnerability. For example, I know buffer overflow. We wanted to see whether the developer correlated the vulnerability when it was working with the buffer overflow scenario. So for half of the developers, this happened. The developer said that they knew the vulnerability, but when he actually was working with the vulnerability, he didn't correlate it. Another interesting scenario was with developers that knew the vulnerability. Let's say they know buffer overflow, and they said that in the end. They correlated. So when they received the puzzle, they said, yes, the problem is we have a buffer overflow here. But when they were asked to do the task, to modify the code, they didn't go to the trouble to fix the code. And this is very worrisome, right? So developers giving maintenance to code, they know that there is an issue, but they don't take any action to make the code secure. And then another result. So most of them were not suspicious about the nature of the study. And most of them said that just priming changed their mindset. Just priming. Not saying anything, but just priming. And we also did a content analysis on their open-ended questions. And we saw that 60% of them explicitly mentioned that priming changed their mindset. So, and I got some quotes here of some of them. Once we were looking for unexpected results, I immediately started thinking of what a dumb or malicious user would attempt to do with my program. Half of them mentioned explicitly that security is not a priority in their environment, in their working environment. Developers look for the most immediate solutions and running with whatever solution Google brings them first. And 34% of them explicitly mentioned that developers only think about common cases. They are not going to think about hidden, unusual cases. And 30% of them acknowledge that security thinking is cognitive demanding. And I thought it was very interesting. It said, this developer said, it's hard to understand the fact that the user input can directly affect the execution of the code, changing what it was supposed to do to something else. So what we got from this study, programming is a cognitive demanding task. And developers, they will focus on functional requirements. So it's a zero-sum game. The time that they are spending on security is time away from shipping functionality to the market. They assume common cases. They trust APIs, libraries of code. And this has to do with attribution, right? If there is a security vulnerability, oh, it's the API. The API has a vulnerability. It's not my code. And we have when I say we, developers don't have any economic incentives for thinking security. Companies, they just want to ship to the market and get the consumers first, and then later they figure out if they breached. Because there are so many breaches with, let's say, Microsoft, Windows, And people are very relaxed about that. They do their patches, so it seems to be working out for them, right? And what we got, what we are researching more specifically since these results is that security information should reach developers when they need it. Not only developers, users, and not the other way around. Not expecting that they will actively make an effort to seek security information, that they read all the guidelines before start coding, or they read the guidelines while coding. This is not how the human beings behave. So trying to change the human, it's probably fruitless. I think it's easier to try to work the way we behave. So, as concluding remarks here for the presentation, challenges in computer security and privacy will only increase. And especially now that we have this very interesting applications of networked computer systems. We have personalized medicine. Now we can have our DNA, our genes completely traced so that doctors can find personalized treatments and effective treatments for our disease. But now the problem is that our entire DNA now can be stored in a cloud computing, and this information can be breached. We can have medical devices implanted in our body to improve our health. We are living the Internet of Things. Everything now is connected, has some processing power, has a sensor. Cloud computing. Our data now is stored in outsourced to hosts and computers that we have no idea and no guarantees of security from the cloud provider. Personal data ownership, privacy. Is data about me, my data, or is just data about me? Do I own data about me? So we're going to have to start having these discussions about our data. And there is no silver bullet for computer security, and the effective solutions, they will be interdisciplinary. They, of course, will involve computer science and engineering, but they will also involve psychology on how to develop solutions that are usable, that people can use. Economics, understanding the attacker's motivations. Maybe it's easier to decrease their motivation than to develop a very complicated, expensive security solution to be installed in a machine. Political. We're going to have to define policy. So we are in a state of cyber warfare. What means retaliate? It's very complicated, right? Because now everything is in the cyber world. And law. So now how can you deal with cybercrime? It's still complicated, especially because attribution. So for example, if my computer is compromised and it's engaged in attacking other computers, should I go to jail because of that, or am I a victim? So it's very, very complicated. And solving this will help us live in this idealized future and secure cyber world where everything that we put online can be deleted and can be forgiven, where we have control of data about ourselves, where we can be inside secure, driverless cars that will cause less accidents than us as humans, where we can have authentication systems. Instead of having passwords, we might have authentication systems that use the signals of our body that are so unique as an authentication, where we leave the Internet of Things in a secure way, and where we can have the benefits of personalized medicine and live better and longer. And also, of course, all of our cyber infrastructure protected. Thank you.